Hello, this is the flight dynamic analysis of Albatross UAV. I'm Meiqi, a third-year aerospace engineering student. This video is a briefing video for the flight test. I'll be doing simulations using Unity. There will be around 5 tests, and the first one is weight and balance. First of all, the center of gravity. We start this test, and as we zoom in, we can see the center of gravity is the black and white little ball, and the long blue bar is the mean aerodynamic chord. The axis is the longitudinal axis of the center of gravity. We can simply change the center of gravity by changing the z-axis on the right hand side. If I put a positive number, it will move backwards. If I put a negative number, it will move forward. As we zoom out, we can see the airplane sits on 3 weighing scales, showing the forces acting on them using unit newtons. As we know, the distance and the forces are shown on a scale. Therefore, we can calculate the moment arm of them in order to find center of gravity. So now, by changing the z value, we can see the numbers on scale are different, since the location of CG is changed. By gathering data in this way, we can put the data into Excel, calculate the moment arm, and we get the calculated CG position, plotting the graph, we calculate the CG position. We could get a straight line from the graph, as shown here. Some of the points are slightly off the line, but it can be ignored. And the point that the aircraft will become unstable is 1.5, as shown on the table, where from 1.5 it goes to become unstable, where I can show on the simulation if I change the z-axis here. The aircraft is stable when 0.15, and if I make it 0.159, it was stable eventually. It is not. To complete this test, the purpose is for the pilot to understand the weight and balance. The next up is the thrust test. There's a load bar here right in front of the aircraft. It measures the force that is acting on it, that is the thrust that the aircraft is making. And when we're ready, we start to work the engine. Once the aircraft hits the load bar, it will start to show numbers. And to turn the flight instrument on to show the RPM, to record further data. So now we're gonna start to work the engine once again. It will eventually hit the bar, and we slowly increase it to 100. As we can see from on the bar, it shows 28 newtons. By doing this for various RPM and record the data, we can plot in Excel and we can get a graph. This helps the pilot to estimate the static thrust. So as you can see from here, we have the thrust actual RPM and the measured RPM. Next up, we are going to do the static response. for the static response here, the runners and flaps are reversed. So by pressing, I will show you in a minute. So by pressing down, the arrows goes up. By pressing up, the arrows go down. Left and right shows this too. For dynamics control response, opening the grapher, we can record some data for analysis. We can adjust it using the elevation. And the aircraft manager, we need to adjust the input mixing matrix to see if it goes the right direction. We can see the arrow here is going the opposite direction. This is just to change the direction of the wind, how the arrow is gonna react and how that make differences to the aircraft. And this one is for us to find the CG and wind speed. Response can be seen with aviation of the elevator. This data can be saved and shown on Excel. We can see on the grapher here. This aircraft was tested on different CG locations with different wind speed. For the plot that we will see later, now just to show how the aircraft changed within the grapher, which is the angle of attack, the elevator input, and heading and roll degrees all changes when aircraft motion change. To analyze data, we find this, we put it in Excel, and we can plot the graphs of angle of attack, elevator input, heading, from these plots we can see that it shows the wind. As the wind speed increases, the elevator response becomes faster and a shorter period reduces in size with a higher damping ratio wind frequency. From this plot we can see the percentage. The next one up is the wind tunnel test. I'll be doing different position of CG and the flap deflections and elevator deflections that I'll show in a minute in the data loggers. We're also changing the wind speed as it comes to the static wind tunnel test. Here you can see the elevator deflections is 0, 20, 40 and flap deflections is 0, 20, 40. CG position is between 0.05 to 0.1. After the simulation, we're going to export this to Excel, and then there's several plots that we're going to be doing. The first one is a CD for flap at 0, and we'll also have CM versus CL. As we can see, the blue line is closest to 0, therefore 0 degrees is the best performance for the CM versus CL. From our data sheet being given, it was suggested that CL max to be 1.2 and 1.4 for 0 and for full flat. For manufacturer data, it will be 30 for max CL over CD. For the last plot, it is CL versus CM for different CG positions. When the graph hits negative region, the aircraft is stable. The last one is the free flight test. This test was done in order to find the trim flight input. Thank you for watching.